The San Andreas Fault has been responsible for some of California's most devastating earthquakes, from the 1906 San Francisco disaster to the 1989 Loma Prieta quake. But according to the latest geological evidence, these historical events may have been just warm-ups compared to what this fault system is truly capable of producing. New research from 2025 has drilled deep cores revealing prehistoric ruptures spanning over 600 kilometers, exceeding the 1906 rupture by 25%. These ancient mega-earthquakes reached similar or even larger magnitudes than anything in recorded history, suggesting that California's seismic future could be far more violent than anyone imagined. What makes this discovery particularly unsettling is how it changes our understanding of the risks facing millions of people living directly above this geological giant. California's underground time bomb. Beneath the surface, nearly 40 million people across California are grabbing their morning coffee, sitting in traffic, or heading to work without giving a second thought to what exists just beneath the pavement under their feet. In Los Angeles, office workers hurry past gleaming skyscrapers that stretch toward the sky. In San Francisco, commuters cross the Bay Bridge while fog rolls in from the Pacific. In San Diego, families stroll along beaches where waves crash against the shore. All of this everyday activity happens above one of the most powerful and dangerous geological features on the planet. While millions of Californians go about their normal routines on the surface, massive forces are building pressure in the rock layers far below them. These aren't small, insignificant movements. The Pacific Plate and the North American Plate are locked in a slow-motion collision that has been going on for millions of years, and the stress from this ongoing battle accumulates every single day. Each year that passes without a major earthquake means more energy gets stored in the rock, like winding up a giant spring that will eventually have to release all that built-up tension. Most people think of the San Andreas as a single crack running through California, but that understanding misses the true scope of what scientists are dealing with. The San Andreas isn't just one fault. It's an entire network of interconnected fractures that spans over 800 miles from the Salton Sea in the south to Cape Mendocino in the north. This system includes 3 major sections that geologists have identified through USGS research, each with distinct characteristics that can influence each other in ways that scientists are only beginning to understand. The complexity of this fault network means that stress doesn't just build up in one location. Instead, pressure accumulates across multiple sections simultaneously, and when one part of the system finally gives way, it can trigger movements along other connected faults. This domino effect has happened before in California's geological history, and recent monitoring data suggests it could happen again. The fault system has been accumulating stress for decades without a major release, and some sections haven't experienced significant movement for over a century. To understand why California sits on such dangerous ground, you need to know how tectonic plates actually work. The Earth's surface consists of massive slabs of rock called tectonic plates that float on the semi-liquid mantle below. These plates move constantly, but at speeds measured in centimeters per year rather than feet or miles. When plates interact with each other, they can push together, pull apart, or slide past each other horizontally. The San Andreas represents the third type of interaction, called a transform boundary, where 2 plates slide past each other in opposite directions. The Pacific Plate moves northwest at about 8 centimeters per year, while the North American Plate moves southeast at roughly 2.3 centimeters per year. This might not sound like much movement, but over millions of years, these plates have traveled hundreds of miles relative to each other. The transform boundary mechanics create a situation where the plates don't slide smoothly past each other like 2 pieces of paper. Instead, they get stuck together along their boundary because of friction and the irregular shapes of the rock surfaces. As the plates continue trying to move, stress builds up in the rocks along the fault line. Eventually, this stress overcomes the friction holding the plates together, and they suddenly slip past each other, releasing all the accumulated energy in the form of an earthquake. This process affects over 40 million people who live in California, many of them concentrated in major metropolitan areas that sit directly on or very close to fault lines. Los Angeles County alone has nearly 10 million residents, and much of the region lies within 50 miles of active fault zones. The San Francisco Bay Area, home to over 7 million people, sits on multiple fault systems including the San Andreas, Hayward, and Calaveras faults. These aren't rural areas with scattered populations. These are some of the most densely populated and economically important regions in the United States. The 2025 monitoring data has revealed patterns that concern scientists who study earthquake activity. Advanced sensor networks now track ground movement with precision that was impossible just a few years ago. These sensors detect tiny changes in the Earth's surface, shifts in groundwater levels, and subtle alterations in the stress patterns along fault lines. The data shows that several sections of the San Andreas system are experiencing changes in their behavior, with some areas showing increased micro-earthquake activity, while others remain ominously quiet. What makes this recent data particularly troubling is that it reveals connections between different parts of the fault system that scientists didn't fully understand before. Advanced computer modeling now shows how stress transfer works between fault segments, and how movement in one area can increase pressure in distant sections. This interconnected nature means that predicting when and where the next major earthquake will occur becomes much more complicated than simply monitoring individual fault segments. The fault system's complexity extends far beyond what you can see on the surface. While the main San Andreas fault creates visible scars across the landscape in places like the Carrizo Plain, most of the system exists deep underground where it's impossible to observe directly. The fault zone itself can be several miles wide in some locations, with multiple parallel fractures that can rupture independently or in conjunction with larger events. Recent deep drilling projects and advanced imaging techniques have revealed that the San Andreas fault system reaches much deeper into the Earth's crust than previously thought. Some sections extend more than 20 miles down, passing through different types of rock that respond to stress in various ways. This vertical complexity adds another layer of unpredictability to how the fault system behaves during major earthquakes. The 2025 research has also uncovered evidence that the fault system is far more dangerous than previous generations of scientists understood. New paleoseismic studies, which examine the geological record of past earthquakes, show that the San Andreas has produced massive earthquakes throughout its history that exceed the magnitude of any earthquake experienced by modern California. These prehistoric events moved enormous sections of the landscape and created surface ruptures that extended for hundreds of miles. But the most alarming discovery came when researchers realized that this massive fault system doesn't behave as a single entity at all. The three-headed monster. Scientists studying the San Andreas fault system discovered something that changed how they understand California's earthquake risk. The fault doesn't behave like a single massive crack running through the state. Instead, it acts like three completely separate entities, each with its own personality, its own history, and its own way of building up and releasing stress. These three sections operate independently most of the time, but they can also communicate with each other in ways that make the entire system far more dangerous than anyone previously realized. The northern section stretches from San Francisco Bay up to Cape Mendocino and has earned a reputation as the most violent of the three segments. This section doesn't mess around when it decides to move. On April 18, 1906, the northern segment unleashed its fury in what became known as the Great San Francisco Earthquake. The rupture started near San Francisco and tore through the landscape for over 290 miles, reaching as far north as Point Arena. Buildings collapsed, fires raged for days, and over 3,000 people lost their lives. The earthquake registered an estimated magnitude of 7.9, but recent analysis of the 1906 event using modern techniques suggests the actual energy release may have been even greater than originally calculated. What makes the northern section particularly concerning is how completely it ruptures when it finally gives way. The 1906 earthquake didn't just crack the surface in a few places. It created a continuous zone of destruction that extended for hundreds of miles, with some areas experiencing ground displacement of up to 20 feet. Fence lines were offset, roads were torn apart, and entire hillsides shifted position. The geological evidence shows that when the northern section decides to move, it moves big and it moves fast. Current monitoring data from 2025 indicates that stress has been building along this segment again, though not yet to the levels that preceded the 1906 event. The central section presents a completely different challenge for scientists trying to understand fault behavior. This segment runs from the San Francisco Bay area down to Parkfield and exhibits something called fault creep. Instead of locking up and building stress like its northern and southern neighbors, the central section moves gradually and continuously at a rate of about 1 inch per year. For decades, scientists thought this steady creeping motion meant the central section was relatively safe because it was constantly releasing stress rather than accumulating it. This assumption turned out to be dangerously wrong. Recent paleoseismic research has uncovered evidence that the central section has produced major earthquakes in the past, despite its current creeping behavior. The geological record shows that this section can switch between creeping and locked behavior over time periods measured in centuries. When it transitions from creeping to locked mode, it can accumulate stress just like the other sections and eventually produce significant earthquakes. The 2025 monitoring data shows subtle changes in the creeping rate that some scientists interpret as early signs of a potential transition toward more locked behavior. The southern section represents the most ominous threat of all three segments. This portion of the fault system extends from Parkfield down to the Salton Sea and hasn't experienced a major earthquake since the last significant rupture occurred between 1721 and 1731. That might sound like good news, but it's actually terrifying from a geological perspective. The longer a fault section remains locked without releasing stress, the more energy accumulates in the surrounding rocks. The southern section has been building up stress for nearly 3 centuries, while the Pacific and North American plates continue their relentless movement. Historical records and geological evidence suggest that the southern section typically produces major earthquakes every 200 to 300 years based on paleoseismic data from USGS studies. The last significant rupture means this segment is already approaching its average recurrence interval. Some sections of the southern San Andreas haven't moved substantially in even longer time periods. This prolonged quiet period means that when the southern section finally does rupture, it could produce an earthquake significantly larger than anything California has experienced in recorded history. According to Yusuf 3 probability models, there's a 93% chance of a magnitude 7 or greater earthquake occurring by 2045. The 3 sections don't operate in complete isolation from each other. Modern seismic monitoring reveals that they communicate through a process called stress transfer. When one section ruptures, it changes the stress patterns in the adjacent sections, potentially bringing them closer to their own breaking points. This domino effect has happened before in California's geological past and could happen again. The 1906 northern section earthquake actually increased stress on the central section, though it took decades for that additional stress to become apparent in the geological record. Current 2025 seismic data shows stress levels in all 3 sections that concern earthquake researchers. The northern section has accumulated significant stress since 1906, though it hasn't yet reached the critical threshold that preceded that massive earthquake. The central section shows signs of transitioning away from its steady creeping behavior toward a more locked state. Most troubling of all, the southern section continues to accumulate stress at rates that suggest it's approaching a critical breaking point. New monitoring technology deployed across California reveals previously unknown connections between the 3 fault sections. Networks of sensitive seismic instruments detect micro-earthquakes and tiny ground movements that were invisible to older monitoring systems. This technology shows that small earthquakes in one section can trigger increased activity in distant parts of the fault system. GPS stations track ground movement with millimeter precision, revealing how stress transfers between sections in real time. The data from these advanced monitoring systems paints a concerning picture of current conditions along the San Andreas fault system. All three sections show signs of increased stress accumulation, and the communication between sections appears to be increasing. Small earthquakes in the central section correlate with subtle changes in stress patterns measured in the southern section hundreds of miles away. Similarly, minor seismic activity near the northern section coincides with changes in the creeping rate of the central segment. Perhaps most alarming is the evidence suggesting that all three sections may be approaching critical stress thresholds simultaneously. This hasn't happened in recorded California history, and the geological record suggests it's a rare occurrence even over longer timescales. Computer models based on 2025 data indicate that if multiple sections were to rupture in sequence or simultaneously, the resulting earthquake could exceed magnitude 8.0 and affect the entire state of California. The prolonged quiet of the southern section becomes even more terrifying when viewed in the context of what's happening in the other two segments. While the northern and central sections show various signs of increased activity and stress accumulation, the southern section remains ominously silent. This silence doesn't indicate stability. Instead, it suggests that this section is locked so tightly that it's not even producing the small earthquakes and micro-movements that typically precede major ruptures. The 2025 monitoring data confirms that the southern section is storing enormous amounts of energy that will eventually demand release in a catastrophic earthquake event. But understanding the true scope of what the San Andreas system can produce requires looking far beyond the earthquakes recorded in human history, deep into the geological record where evidence of the fault's most devastating ancient behavior lies buried. When the Earth rewrites history. Scientists working in 2025 have been digging trenches across California's landscape, but they're not looking for buried treasure or ancient artifacts. These researchers are hunting for something far more valuable and terrifying, evidence of earthquakes that happened thousands of years before humans started keeping written records. Their discoveries have revealed that the San Andreas fault system has produced catastrophic events throughout its history that make modern California earthquakes look like minor tremors by comparison. The detective work these paleoseismic researchers perform requires incredible patience and precision. They dig carefully planned trenches that cut directly across fault lines, exposing cross-sections of rock and sediment layers that have accumulated over thousands of years. Each layer tells a story about what was happening on the Earth's surface when it was deposited. Scientists look for specific clues that indicate when major earthquakes occurred: offset rock layers where the fault suddenly shifted, broken and displaced sediment deposits, and organic materials like charcoal and plant remains that can be radiocarbon dated to establish precise timelines of past ruptures. The methodology involves examining every detail visible in these trench walls. When a major earthquake occurs, it leaves unmistakable signatures in the geological record. Rock layers that were once continuous get broken and offset by the fault movement. Sediment deposits show evidence of sudden disruption and displacement. Sometimes entire sections of the trench wall show evidence of multiple earthquake events stacked on top of each other, creating a timeline of seismic activity that extends back thousands of years. What these 2025 investigations have uncovered defies what most people understand about California's earthquake history. The geological record reveals evidence of prehistoric mega-earthquakes that released energy far exceeding anything California has experienced in recorded history. These ancient events didn't just shake buildings and crack roads. They fundamentally altered the landscape across hundreds of miles, offsetting ridges by tens of meters and redirecting ancient river channels. The scale of these prehistoric earthquakes becomes clear when scientists examine the geological evidence of surface ruptures. The 1857 Fort Tejon earthquake, which ranks among California's largest historical events, created a surface rupture that extended about 350 kilometers along the fault line. The maximum ground displacement in some areas reached 9 meters, enough to completely offset roads, fence lines, and any other human-made features that happened to cross the fault. Some paleoseismic ruptures approached similar distances of 350 kilometers, longer than most historic events, but representing the true potential of this fault system. These ancient mega-earthquakes left permanent marks on California's topography. Geological evidence shows that some prehistoric events shifted entire hillsides and ridge lines by distances measured in tens of meters, rather than the single-digit meter displacements typical of modern California earthquakes. River systems that had been flowing in the same channels for thousands of years were suddenly redirected when fault movement created new topography. Valley floors were uplifted into hills, and hills were dropped into new valleys. The landscape that exists today in many parts of California reflects the cumulative effects of these massive prehistoric seismic events. The timing patterns of these mega-earthquakes reveal something particularly concerning about how the San Andreas fault system operates over long time periods. Rather than producing large earthquakes at regular intervals, the geological record shows evidence that the largest earthquakes tend to occur in clusters. Trenching data reveals 4 paleoseismic events that exceeded current recurrence intervals, suggesting periods of intense seismic activity followed by longer quiet phases. The southern section of the San Andreas fault shows particularly strong evidence of this clustering behavior. Paleoseismic studies indicate that this section has experienced 7 major earthquakes over the past 1,000 years, with timing patterns that suggest these events don't occur randomly, but follow recognizable sequences related to how stress accumulates throughout the fault system. Surface rupture evidence from these prehistoric events extends for distances that challenge modern understanding of fault behavior. While the 1906 San Francisco earthquake created a continuous rupture zone extending about 470 kilometers, geological evidence of some prehistoric events shows rupture zones approaching the maximum observed lengths of individual fault segments. These massive ruptures involved movement along multiple connected fault sections that demonstrate the true scope of what the San Andreas system can produce. The energy release from these prehistoric mega-earthquakes carved permanent scars into California's landscape. Ancient lake beds show evidence of sudden uplift that drained entire water bodies. Mountain passes were created when fault movement dropped sections of ridge lines below the surrounding peaks. Coastal areas show evidence of sudden elevation changes that moved shorelines by significant distances in single earthquake events. These landscape modifications happened in minutes or hours, rather than the gradual geological processes that typically reshape terrain over millions of years. Current conditions along the San Andreas fault system show disturbing similarities to the geological signatures that preceded previous major earthquake episodes. The southern section hasn't experienced a major rupture in over 300 years, which places it well into the time range when previous clustering episodes began. Stress measurements from 2025 monitoring networks indicate that multiple sections of the fault system are approaching critical thresholds simultaneously, a condition that hasn't existed since the last major clustering episode several centuries ago. The possibility that California may be entering another period of major earthquakes represents a seismic threat unlike anything the state has faced in its modern history. The prehistoric events revealed by 2025 paleoseismic research suggest that when the next major earthquake cycle begins, it could involve multiple large events occurring within decades of each other. These events would affect the entire state rather than just regional areas, and their cumulative impact would exceed anything that current emergency planning and building codes are designed to handle. The geological evidence points toward a disturbing conclusion about California's seismic future, but the full picture of what makes the next major earthquake potentially more devastating than anything in the prehistoric record requires understanding an unexpected factor that most people would never connect to earthquake activity. This unexpected factor lies hidden beneath the desert waters of Southern California's most overlooked lake. Most people driving through the Imperial Valley probably don't think much about the Salton Sea, that odd inland lake sitting in the middle of the desert about 150 miles east of San Diego. The lake looks pretty unremarkable from the highway, just another body of water in a landscape that doesn't seem like it should have any water at all. But this strange lake holds the key to understanding why the next major earthquake on the southern San Andreas fault could be more devastating than any seismic event in California's recorded history. The Salton Sea that exists today represents just a tiny fraction of what once covered this desert valley. For thousands of years, an enormous lake called Lake Cahuilla filled the entire Coachella Valley and extended deep into Mexico. This ancient lake was absolutely massive compared to what visitors see today. Where the current Salton Sea covers about 350 square miles with a maximum depth of around 50 feet, Lake Cahuilla stretched across more than 2,000 square miles and reached depths of 300 feet in some areas. The ancient lake held approximately 40 times more water than today's remnant, creating a body of water that would have rivaled some of the Great Lakes in size and depth. Lake Cahuilla didn't maintain constant water levels throughout its existence.